We're going to do this a little bit differently since it's a co-award. We'll do our standard Mutt and Jeff. We'll kind of interrupt each other and just talk through things as we go. Wanted to start with a little bit of historical context about what National Instruments does so that it can frame what we do specifically in our roles. In 1986, a rather young-looking Jeff Kadowski created a programming language called LabVIEW. At that time, the way scientists and engineers actually did their work, you were limited essentially by your physical interaction with your instrumentation. And so I was pleased to see several examples in the previous speakers of LabVIEWs in their usage in their videos last night. JC in particular, I know I saw lots of images. Duncan actually can tell a little personal story about the relevance of JC's work if you want.
Well, yeah, as JC was doing his presentation, I was particularly excited about having seen LabVIEW in his work because his list of research topics read like what research I need done in my family. You know, my wife has chronic pain and has a neural stimulator. I'd love for her to have a closed loop controller, and JC says I can have it in a couple years. I'm looking forward to that. I have in-laws who've experienced some of the cancers he's researching. My son's struggling with gastropariasis-like issues, so please let me know what you need in LabVIEW, and we'll get that taken care of.
And so what you'll see as a theme for us is that unlike, I think, some of the previous researchers, we are tools providers to you. It's our life mission to enable you to be more productive, to solve more problems more quickly. So if JC can help Duncan's wife, that's fantastic. If you're limited in your research by the speed at which you can sequence a genome, well, then we want to help you make that faster. And so what they started with was science and innovation is limited by the rate at which your instrumentation and analytics can run. And so as you have advancement in instrumentation, you have advancement in the science you can do. And so what Dr. T and Jeff Kadowski did was, let's take commercial off-the-shelf technology, let's take this idea of these sensors and actuators, and let's take a nice programming language that enables domain experts who are not computer scientists to really automate their research. And so it is the mission of National Instruments to enable you to be more productive, leveraging standard PC technology and a programming language to make innovations happen like we've seen here so far. So specifically, in 1986, I was around 14, so we clearly didn't participate in the innovation of LabVIEW itself. Wanted to highlight that National Instruments is investing in this particular software product for over 24 years. How many lines of code?
A few million.
So it's a few million lines of code. It's a 40-some-odd product lines. It's rather complex. I like to think of it as a evolving and growing organism. It's not exactly biological, but it feels like it sometimes. We've been doing some major breakthroughs. I think we're gated by what the silicon manufacturers do in industry. So as things like field programmable gate arrays have come out, we've had to look at how we map our programming language to leverage that semiconductor technology. So there's this very nice relationship of evolution in the computing space, evolution in the language space, MEMS, sensors, actuators, and what we do, where we're all kind of working together to push each other forward on a continual basis. So there's a trend in the semiconductor space where we're no longer getting the Moore's law that we've had for a while. And so we're all running smack dab into this issue of we don't get a free ride in software anymore. And so for years, you could get faster programs simply by the semiconductor manufacturers making faster processors. And that's basically on the cusp of stopping. And so now I think the onus is going to fall to the software side, and we'll go into a little bit of detail about how you have to take a software program and map it to parallel processors in a little bit. So this is just a catalog of areas highlighted in yellow where Duncan and I directly guide the research and direction of a fairly large 300-person research and development organization. So to get grounded, LabVIEW itself was started with the idea of, okay, let's let engineers leverage this computer like financial analysts have done with spreadsheets. And so what the idea was is you have a basic unit on your computer of a front panel and a block diagram. And it's a way in the front panel that you can just visualize your data. I don't know how many of the presentations today someone has a graph or a chart of their scientific research, only this is a live interactive graph or chart that can be backed by data that you get from the real world. But then you have to do something with the data that you've got. You want to analyze it. You want to check it to see if it's over a certain range. You want to look for these patterns in the gene sequences that you guys have all been showing. So you have to write some degree of logic to do that. What we found is that there's an impediment to leveraging your computer, which is you're required to be a computer scientist to write programs that were sophisticated to do this sort of analysis. Only I myself am a computer scientist. Most of us have no way of being able to step into y'all's domains and actually write the analytics. That's what you've been researching. That's your area of expertise. And so we wanted to remove the impediment of having to work with guys like us for you guys to do your research.
Believe it or not, a large amount of information is lost when you try to go from an expert in cancer research to a guy who knows how to write a program for him.
Speaking for myself, I'm pretty sure I didn't translate all of the presentations you guys gave and walk away as an expert in those areas, for sure. So from a language model point of view, LabVIEW is homogeneous data flow. Data flow actually came out of electrical engineering space, it's been around for a long time. This follows a specific order of execution that maps naturally to the way that people think. And I think it's actually its graphical nature and its spatial nature that makes it intuitive for everyone, even non-programmers. It's a series of blocks that you stitch together, and if they have a connection, then they pass data to each other. And it runs left to right. And so in space, you look at it and go, oh, that happens, and then that happens, and then that happens. And it's a very natural way that we see the world around us anyway, because we're directly manipulating things in space and relationships through our whole lives. Hierarchical in the sense that once you have something that you've created in this block diagram language and you want to reuse it, you can create a little subcomponent and reuse it. It's a form of leverage. It's required in most computer languages. I'm not going to go through every specific aspect of its language model. I think one of the key points is that it's a fully synthesizable language. And this is really where Duncan and I spend a vast majority of our time, is our software language is gated in what it can accomplish based on the semiconductor technology that's out there that it runs against. As things change in those chips and in those FPGAs and in whatever special cell processor comes out, we have to map the basic algorithm that you have written to run against that hardware. And the semiconductor industry, thankfully, is not standing still, and so we have a built-in job security function. One other key element of LabVIEW, and I think this comes from its roots in the test and measurement space that Dr. T started in, and the goal of enabling science and engineers, the language has to be tightly aware of the real world. The real world has an absolute time in it. When you're looking at most languages in computer science, they like to abstract away as much of time, I/O, as they can, because they want to run independent of time. That was actually one of the stated goals of some of the computer architectures of the past. If you're trying to monitor something like the heart rate of an animal and you're unaware of and can't synchronize very precisely in time, the fidelity of the control that you can do to close any loop, say the pain loop that JC is closing, is very poor. So you need very precise timing.
So a key attribute of our platform is this focus on solving problems where you need to interact with the real world, whether it's measuring, controlling, or in any way affecting or understanding the world around you. Well, a key attribute of the real world is that it's concurrent, it's parallel. You don't walk and then chew gum, then walk. You walk and chew gum at the same time, and myriad other things. So the degree to which your language and your tools can accurately deal with the real world is the degree to, in some sense, which it can deal with concurrency. That's amplified by the trends that we're seeing in computing technologies, where as Moore's law is asymptoting in one sense, people are turning towards parallel realizations, whether in multi-core CPUs, GPUs, or in field programmable gate arrays. So a key advantage, as Dave alluded to, of LabVIEW and of data flow languages in general, is that they don't over-constrain the problem that you're describing. When you're drawing your system or describing your system, the only real constraints on how things can execute is the need to pass causal data from one computing element to another. You don't have artificial constraints like, I just happen to write this statement before this other statement, which you'll have quite often in sequential textual languages. Furthermore, you need to be able to naturally express and understand the parallelism in the language, and our tools need to be able to efficiently reason about the language and map those to the computing targets that Dave was talking about. So you can see on the screen here one example that we've picked that's a fairly common numerical example is a matrix vector multiply. And if you were expressing this in a textual language, it might be a bit obscure for you to understand. But I think if you look at that image in the left corner, you can get some immediate visual intuition that we have a program that's decided to split the problem up 8 ways because there's 8 blocks and then bring the results back together. Because the flowchart idea, the visual depiction, is a thing that is a close mental model to what a scientist or engineer might draw on a whiteboard if they were trying to explain how I was going to break a problem up into 8 pieces and then bring the pieces together again. And then our compiler needs to be able to take that. That's the tool that takes a language that expresses the problem you're trying to make a computer do and actually causes it to run on your computing device. Well, in our case, we take the high-level description of the program that's in an intuitive form, and our compiler translates it into machine instructions when you're talking about CPUs and parallel processors that can then be dynamically scheduled and run through this mechanism we call the run queue. Or if you get into reconfigurable chips, we can use a similar tool chain as a backend to actually take your described problem and literally turn it into a circuit that will truly operate in parallel without any scheduling at all. The key is that needs to happen behind the scenes without the domain expert who's trying to solve a problem actually having to understand that that's all happening, and that's what we do. So in terms of being able to express your problems, there are many types of parallel things you might want to express, and we're just showing a few examples here of the idea of wanting to pipeline an operation where you have several, you can think of it as wave fronts of work happening, where as soon as one stage of the pipeline gets done, somebody else is queuing behind. Or you may have many actors all doing the same thing, wanting to share data with their neighbors. You can see the picture in the bottom left there. Or you may just simply have the idea of wanting to take some data, break it up into pieces, and do the same operation many times. The key idea here is it has to be expressed in a way that's easy for you to depict and then understand and explain with people. Then on the reasoning side, you need a compiler that operates on that. Well, here, our data flow nature gives us another advantage because we're actually already closer to the information that the compiler needs in order to be able to produce a program that runs. Traditional textual sequential languages have to go through stages where they translate characters into sets of tokens, and those tokens build up these parse trees. And once you get to that point, you can start doing analysis to determine how data flows from one function to another. We start with the data flow graph. So that's a whole series of work that the compiler doesn't have to do. And in fact, some of our recent evolution of the compiler, introducing intermediate stages where we're doing additional reasoning and analysis to optimize the performance of your system, can take advantage of information expressed by the user within the data flow graph that's analogous to providing hints to a compiler about how you might want to generate your code. So that was a fairly low-level element of our platform, just one area that we're innovating on, the compile chain and the language. To me, when I think what's the real innovation here, there's a whole collection of innovations that went into the 40 different products and elements that make up the LabVIEW family. But to me, the biggest innovation that's resulted from it is a tool usable by domain experts to span a continuous spectrum from kindergarten, K, we call it, through rocket science. So whatever your science or engineering application that you're trying to do that's got some connection with the real world, whether it be a student having their early experiences with trying out science and engineering through a rocket scientist. Or in the case you see up here, a kid playing with Lego Mindstorms, where we've partnered with Lego to provide the software that goes with their hardware to enable children to build their own autonomous robots, all the way up through what is often called the most powerful instrument on Earth, the Large Hadron Collider. We're using the same fundamental programming model and fundamental software to solve that continuum of problems. So to dive into one end of the spectrum, the K side, we've collaborated with Lego on quite a few things. Probably the lowest age group is a product called WeDo, which is even more simple than the graphical programming software we did with the Mindstorms you can buy in Toys R Us. It goes down to children as low as 7 years old. Actually, we'll show you a 6-year-old. And what it allows is for kids to get very early introduction to hands-on engineering and science. And in this particular case, building robots, little machines. An example would be this little alligator that you see here, where the student is actually programming the behavior of when I put my finger in the mouth, the thing will chomp. And we have a little video here that we'd like to show you to illustrate what a young child is able to accomplish with this software.
Hi, my name is Kai and I'm 6 years old. Today, I'm going to show you my cool cheerleader robot. And I'm going to write a program to make it do some stuff. I just want it to jump up and down and write some words on the screen. First, I'm going to have to open up the program and start doing some stuff here. Next, I'm going to do the repeater. And then I'm going to make the motor turn that way. Now I want to make words come on the screen. I think I want to say hello. I want to make pictures. Get the pictures in. Now I'm done with the program. Now all I gotta do is press start. See, when they move, my picture changes too. My dad says this is parallel programming, but I just think it's fun. Do you think they'll let me work on LabVIEW when I grow up?
So you can see, that's just a little picture of what we're trying to achieve with kids, which is unlocking their creativity, letting them play and experiment with engineering and science. And really, that's what we're trying to do with the rocket scientist as well. So to continue the theme, rather than robots, I'll stick with the theme of, rather than rockets, I'll stick with the theme of robots. At the other end of the spectrum, using that same basic metaphor and language and tool chain, we're enabling the world's researchers to create a panoply of fascinating experimental robots, ranging from snake robots that mimic living snakes in order to be able to scale things like poles, the blind driver challenge, which they were creating sensors that truly didn't drive a blind person. They actually enabled a blind person to feel and understand the world around them so that they were able to actually pilot the vehicle, to things like the Vecna Bear, which is a robot designed to actually go rescue soldiers from the battlefield so that somebody else doesn't have to go run out in the gunfire and grab the person. But the range of applications is far beyond robots. That's simply an illustration of one area of great passion for us that we built our robotics module to help make happen. So one of the key evolutions of our tool chain and our language as we got into larger sets of problems beyond our basic test and measurement heritage is continuing to be able to model the problems to be expressed the way the engineer thinks of them. So beyond our fundamental data flow paradigm, or we call it model of computation, we've introduced additional models of computation to represent other ways that engineers and scientists think about things. For example, state charts to depict state-based systems where you're thinking about a system that's going from a mode to another mode, or dynamic control models where you're thinking more about a physical model in a textbook, say from a controls textbook, and all of those things then being able to blend together in a common tool chain that goes down together through a common compiler that we talked about, an optimization layer, and through that is able to then target whichever of the computing devices you need in order to make your problem come to fruition. And with that, I'll hand it back to Dave to get into our embedded side.
So this is an image taken from Dr. Sanjivani Vincentelli at Berkeley. You'll notice it's an hourglass-ish shape, and it kind of matches this image that Duncan was talking 5 minutes, okay, here. So the picture that you saw was NI's version of Dr. Sanjivani Vincentelli's hourglass. And it captures his research that describes the world of embedded computing really as follows, which is there's an infinite, really, application space of problems that you all are trying to solve. So there's some, you're going to write an algorithm, you're going to write some code, it's going to do something. This is the set of things that you might write. That software, in a perfect world, would run as fast as you wanted, as quickly as you wanted, on as cheap a hardware as you could find. But unfortunately, that's not the world we live in. You have to actually then also have a set of hardware that you understand, that you then go through and select cost, performance, power consumption, trade-offs. That's what's called the architectural space. So you need a way to describe your applications. Typically, that's a computer science, that's a language. And then you need a way to describe your architectural space, which is some computing platform, typically a combination of a processor, some sort of FPGA, maybe GPUs, whatever it happens to be. And then there's a mapping process. You take your algorithm and its expressed goals, speed, rate, size, whatever, and you want to map it to some instance of something in the hardware space that then in union is a combination of hardware and software that satisfies your goal. So there's a tremendous amount of research that we do, that Berkeley does, as well as tons of folks in the semiconductor space, for formal languages to describe the characteristics and capabilities of the architectural space. And then there's a ton of work that we do as language designers. Duncan and I particularly both specialize in the translation of the expressed application space to the architecture that you're running against. And so then we also union that with another view that came out of Berkeley, which is a Y chart. There's some contention as to who actually created it, so I listed every possible creator, just to be safe, which was, again, this notion of a cycle of development that you want to accelerate your end user's productivity, which is express logic devoid of specifics of hardware, easily explore the hardware space, rapidly combine those two, see how your application is going to perform, and then feed that cycle back. It's kind of intuitive, but a lot of tool chains fail to deliver on that. One very specific example of what is a synthesis of a high-level block diagram data flow language like LabVIEW is to a type of technology called a field programmable gate array. And really, from our point of view as a data flow language, FPGAs represent an ideal execution platform because they're fundamentally asynchronous at their underlying nature. When you look at most CPUs, they're unfortunately sequential, at least in the single process that's executing. And so what we've done here is an example of, let's say you had some basic logic that you expressed here on the right. We have a methodology for taking this asynchronous platform, translating your high-level representation to a series of what's called VHDL statements that then execute on the FPGA. And so the number of people who could actually implement the logic on an FPGA is very limited. It's a specialization within electrical engineering, and that's a domain very far removed from chemistry, biology, physics, and so on. And so we've enabled physicists to solve some pretty amazing problems, expressing logic in a way that makes sense to them, and then running it at speeds and rates that they could never achieve without hiring a design team. And so we feel like that's one of our major innovations in helping especially high-speed implementations. How much time do we have left? 1 minute? Okay. So we'll end quickly here. There is a problem that we're starting to run up against, which is as the hardware architectures out there are starting to get more and more complex, and generally the problem space is getting more complex as well, the issue of safety and correctness of automated systems, especially if you're talking about things that are implanted into the body to do a closed-loop control system, you want to guarantee that the software implementation that's running that controller is correct. And there's this fundamental trade-off, and I think it's the nature of the universe, in terms of this axis here of expressiveness versus analyzability. And all that really means is the more stuff that we let you write your code to do, the more flexible it is, the more problems you can solve, the harder it is for a language to guarantee that what you've said is actually going to work. So you start constraining down the number of things that you let someone do in your software, and then they're solving fewer and fewer problems, but you can guarantee that it's right. Kind of makes sense. You do very little, it's easy to prove that what you're doing is right. The more you do, the harder it is to prove. So we're spending a tremendous amount of research energy in trying to find a sweet spot in provably correct by construction code that we can guarantee won't deadlock, won't fail, won't cause a problem in your closed-loop controller for your heart. But you can still solve complex enough problems that it's relevant to the market. And then I'll go to the final slide. One of the things, and this is really what I've seen here and what we see every time we interact with scientists and engineers the world over, these are the engineering grand challenges as identified. It is incredibly rewarding for us as tools provider to see that our customers use our tools to solve problems in all of these spaces. This group represents people solving these problems, and it really is satisfying for both of us to work at a company where we're really trying to enable you to make the world a better place. So thank you. Questions?
Hello, my name is Klaus Wilke. I'm a computational biologist at UT Austin. And in my area, we see this trend that we're trying to make all the tools that we're developing freely available as much as we can. And so one concern that I see with your approach is if I were to use LabVIEW to develop a program, would I even be able to show my program to a colleague who doesn't have LabVIEW? And would I be able to put my program on the web and say, people download this program, you can use it, and also would I be able to use it 20 years from now? What are your views on this?
So a couple of angles on that. The first is if you build a program in LabVIEW and you want to distribute it freely, you can do so. It has no limitations on distribution, so if you want to share it with colleagues and wherever, that makes sense.
And in fact, there are probably tens, if not hundreds of thousands of such virtual instruments, we call them functions, being shared by people both on our site and third-party sites and in academia as well.
The second part of that is how will LabVIEW be around in 20 years? It's been around for 25 years. I think the short-term answer is it's a linchpin in our corporate strategy, and it is the basis of tons of our product lines. As long as National Instruments is around, LabVIEW will be around. That's one answer. I think the longer-term answer, and I think we'll eventually get there, is I hope one day that we're broadly successful enough that we license the language and forms of it into the public domain, which other vendors have done, Microsoft as an example, of languages that they create.
Very interesting approaches, but how do you make up a team between the biologists and you guys? How do you begin? You're really going after a big problem. You need, what we know in NIH terms, preliminary data, which can take huge amounts of time and money to generate. How do you go through that whole process? Do you have a plan for it, or is each case individual?
Also, a key part of our idea is actually to provide tools to the domain experts so that it's not necessary for us to be a part of the equation in order for you to solve your problem. So the intent is primarily that we're providing tools that are easy for you and your colleagues to understand, where the domain experts can actually literally be within their research team doing the description of the acquisition task, the control task that needs to be done as part of the research, and iterate on that as rapidly as possible. Then, for very large challenges, we are increasingly getting involved, our company, in system engineering efforts where we partner with both folks in academia and industry to tackle some of the really hairy, really challenging problems that are out there.
Yeah, an example of that would be like the tokamak on the slide. If you can bring the slide back up. We worked with the Max Planck Institute to help them implement some control algorithms for a tokamak controller. I mean, these are, we do recognize that there's a spectrum of, within your team of biologists, you can program some degree of systems. But when you want to scale it all the way up to solving some of the world's largest outstanding, control problems for physics, that yes, you can involve us.
Yeah, I'll give you an example of the other. The Urban Grand Challenge, which is one of the robotics projects I didn't talk to, the Virginia Tech team, which placed third behind Carnegie Mellon and Stanford, but right ahead of MIT. Their team consisted of nothing but really mechanical engineers, none of whom were experts in programming. Using our hardware and our software, they were able to, without enlisting any computer scientists, electrical engineers, or computer engineers, completely define their system and make a very successful self-guided city driving robot. And in fact, the flexibility that they had using that tool chain and having the domain experts actually directly doing and describing the problem enabled them to be at the field site tweaking the behavior of their system based on information that they'd learned recently up to the very last minute and actually have their system still run, where the teams that were using much larger computing power but a more traditional approach where there's a separation between the scientist or the engineer and the programmers, they wouldn't have attempted that for all the money in the world.
Thank you.